So if a function is continuous on an interval from A to B, then it's Riemann integrable on that interval from A to B. And in some sense, many details to follow, that's sort of the punchline. So what we're going to do now is introduce the idea of a weight of a set. These are going to be small sets. And we'll ultimately see that the previous result gives, in some sense, a classification of Riemann integrable functions. What we'll do in the graduate real analysis is take this idea of measure and really run with it. What we're about to do is consider sets of measure zero, a topic that I'd be a little bit surprised if you touched on in senior level analysis. It's in the Kirkwood book. It's not in many of the senior level analysis books, but it's in the Kirkwood book. That's one reason I like the Kirkwood book. But we can do this measure zero that we're about to do without getting into all the intricacies of measure theory. So the following is not measure theory. The following is measure zero. And a whole bunch of stuff can go wrong if you transition from measure zero to positive measure. So that's why it can be covered in this measure zero stuff can be covered in a senior level analysis class. But you can't cover regular measure theory reasonably, in my opinion, in a senior level class. So first definition, the Lebesgue measure of an open interval, AB, is simply its length, B minus A. The measure of an unbounded open interval is infinite and will denote the measure of what we've defined. The measure of an open interval is M of I, measure of I. There's lots of sets other than open intervals, as we'll certainly see in graduate real analysis. We're about to use open intervals and their measures to define what we mean for a set to have measure zero. When we do measure theory, we'll use open intervals and their measure to define, in a sense, the measure of any set of real numbers. Yeah, lots of details to follow on that. But here, what we mean to say a subset E of the real numbers has measure zero is that for all epsilon greater than zero, there's a countable collection of open intervals, I1, I2, and so forth, such that E is a subset of the union of those capital I's sub lowercase i's, I equals 1 to infinity, and the sum from I equals 1 to infinity of the measure of those open intervals is less than epsilon. Okay, so what we've done is taken set E and covered it with open intervals, a countable collection of open intervals. Certainly that can be done. The whole real line is an open interval. And then we've added up, we've summed the lengths of those intervals, the measures of those intervals, which are their lengths. Why countable number? Well, it wouldn't make sense to do a summation unless we had a countable number of things. So that's why countable number. So that's the definition of measure zero. I can't give you a whole lot of insight on it other than to say, no matter how little epsilon is, you can cover this set E with open intervals, the sums of whose length is less than epsilon. So that can't be a big set E. E couldn't be like the interval from 0 to 1. You cover it with open intervals, you're going to cover it with a bunch of sets, the sum of whose length is at least 1. So being a set of measure zero, wink, quite informally, means it ain't a very big set. I'm not talking big in sense of cardinality. We'll see that cardinality interacts with measure in a very poor way. Not much can be said, one little thing can be said about the interaction of the cardinality of a set of real numbers and the measure of the set of real numbers. And we'll say it, we'll even prove it. But this set E with measure zero, in some sense, it can't be very big. Okay, the following are simply straight from the definition of measure zero. A subset of a set of measure 0 has measure 0. If I took a subset of set E, and knowing set E is of measure 0, I could cover the subset with the same collection of open intervals for given epsilon, and we're good to go. So certainly subsets of sets of measure 0 are measure 0. The union of a countable collection of sets of measure 0 is a set of measure 0. Follows from the definition of measure 0. Let's go through a proof of a special case of that. So, countable collection of sets of measure 0, union to give a set of measure 0. We're going to become infatuated with countable unions and maybe countable intersections. And certainly countable things when we have to add up stuff like this, when we have to sum measures, we'll definitely be interested in countable things. So instead of proving theorem 6.9 in all its generality, let's give a proof of the following. A countable set has measure 0. So we were talking about a countable collection of measure 0 sets there. Here we're simply talking about a countable set. I said cardinality and measure are not really very closely related. There's one result, this is it, that relates cardinality to measure. Countable sets of real numbers have measure 0. Guess what? Uncountable sets can also have measure 0 or measure not 0. So there's not a good relationship between cardinality and measure. Countable sets have measure 0. I see students get in their heads, even in this graduate level class, to think about the converse of that as true. No. A set can have measure 0 and not be countable. We'll dig into that in more detail later if you've encountered the Cantor set. The Cantor set is a set of measure 0, which is uncountable. So the relationship is, if the set is countable, then it has measure 0, full stop. There's no if and only if. There's no observation that uncountable sets don't have measure 0, nothing. This is the only relationship we have between cardinality and measure. And it's a pretty weak one. Okay, here's how the proof goes. We want to take this set and cover it with little open intervals, the sums of whose length is less than some given epsilon. So let epsilon be greater than 0, and let A be the countable set. Say the elements are A1, A2, A3, and so forth. So there's a first one and a second one, and so forth. Define interval capital I sub lowercase I to be element of set A, lowercase a sub I, minus epsilon over 2 to the I plus 1, comma, a sub I plus epsilon over 2 to the I plus 1. So what's the measure of this interval? What's its length? Well, it'll just be the difference of the endpoints. It'd be epsilon over 2 to the I. Take the difference of the endpoints. That'll give you the measure of that interval. The measure of an open interval is its length, so we're good to go on that. So the measure of capital I sub lowercase I is epsilon over 2 to the I. Also, every element of set A is contained in one of these intervals. Element A sub I is contained in interval I sub I. So if we'll union up over I equals 1 to infinity, capital I sub lowercase I, union up all these intervals, then that's an open cover of set A. A cover of set A with open intervals, not just any open cover. And the measure of each of those constituent intervals is epsilon over 2 to the I. So if we add up from 1 to infinity, the measure of the intervals, that is, add up their length, epsilon over 2 to the I, we can bring the epsilon out front, we get a sum from 1 to infinity of 1/2 to the I. Why, that's a geometric series. It's a geometric series with first term a half and ratio a half. It sums to 1. It's 1/2 plus 1/4 plus 1/8. It sums to 1. So there's how we took care of the infinite part right there. And we get an epsilon out. So look what we did. We took set A. We covered set A with open intervals. The sums of whose lengths is, I guess we strictly speaking, we got out equals epsilon, good enough to show that the measure of set A equals 0. So any countable set has measure 0. There was some infinite stuff in there, but still, because of the countability, we were able to go through and establish that the measure of a countable set is 0. Had we had a countable collection of sets of measure 0, we would have covered that first set with a countable number of intervals of length epsilon over 2. You can do that by the definition of measure 0. We would have covered the second set by a countable collection of intervals, the sums of whose length is epsilon over 4, and then epsilon over 8 for the third measure 0 set, and so forth. Taking all those intervals together, that would have been an open cover of the whole set, summed everything up, and still got an epsilon out. It's a similar trick to what we did here, just a touch more complicated for the theorem. But this illustrates the idea. That'll do for now. Not that that result is particularly interesting. It really is a theorem that we'll use later on. Comments about cardinality and measure, they're not closely related. Corollary 6.9 is really all you can say about measurables. Measure versus cardinality. There exists an uncountable set that's also of measure 0. It's the Cantor set, the Cantor tertiary set. We'll look at that in more detail later. We'll look at it in the graduate class too. Okay. So what we want to do is back to a conversation about necessary and sufficient conditions for Riemann integrability is we want to describe how continuous a function has to be Riemann integrable. If it's straight up continuous, it's Riemann integrable. But you know from calculus 2, if it has a discontinuity at a single point, like a jump discontinuity, it could still be integrable. If it's too badly discontinuous, like the function that's, say, 0 on the irrationals and 1 on the rationals, the Dirichlet function, sometimes called a salt and pepper function. That one's so discontinuous, as you see in calculus 1, maybe it's not Riemann integrable. So there's something to do with how discontinuous a function can be and still be Riemann integrable. The punchline is this is what the Riemann Lebesgue theorem says. I can make sense out of it now. It ties together this idea of measure 0 and Riemann integrability. The Riemann Lebesgue theorem will say a function in the appropriate setting to discuss Riemann integrability is Riemann integrable if and only if the set of discontinuities has measure 0. So it can be discontinuous, it can be wildly discontinuous, but it can't be too badly discontinuous. And how badly discontinuous can it be? That's where the measure 0 stuff comes in. It has to be discontinuous on a set of measure 0. More discontinuous than that, Riemann can't handle it. But I bet you Lebesgue might be able to handle it. And that's what we're doing, is motivating a consideration of Lebesgue integration, Lebesgue measure and Lebesgue integration. Okay, this seems to come out of the blue, the oscillation of a function on a set, but this will tie into continuity, and we'll use this in the proof of the Riemann-Lebesgue theorem. The oscillation of a function f on a set A is defined to be the sup of the absolute value of f of x minus f of y, where x and y are chosen from set A and from the domain of the function, of course. So oscillation tells you sup how far apart, in a limiting sense, you can make the output values from function f. How far apart the function values can be as the input values range over set A and the domain of the function. We're actually more interested in the oscillation of a function at a single point, and that's defined as follows. So the oscillation of f at fixed point x is the limit as h approaches 0 from the positive side of the sup of the absolute value of f of x prime minus f of x double prime. So it's a distance between function values again, well, a sup and then a limit, such that x prime and x double prime are chosen from the interval x minus h to x plus h intersect the domain of the function. So this is an interval centered at x. Ultimately, it's not going to be a very wide interval because what we're going to do is take the oscillation on this set and then take a limit as h approaches 0 from the positive side because of the nature that that interval has been described. So this is denoted the oscillation of function f at point x, and it's the oscillation at a point that we're interested in. So if the function had a jump discontinuity, for example, at point x of, say it had a gap in the graph of the function of size 1, this oscillation would be 1. If it's a continuous function, as we'll show shortly, that means the oscillation is 0. So oscillation of a function at a point is defined as given here, limit and a sup. So there's sort of two moving parts in that. And oscillation is closely related, there we go, to continuity. Theorem 610 says a function is continuous at a point in the domain of a function if and only if the oscillation of the function about that point equals 0. And the argument really just follows from the definitions. Suppose the oscillation is 0, we want to show the function's continuous. All right, let epsilon be greater than 0. We want to show continuity at point x. X is a given point, a fixed point if you like. Well, then there's a delta based on epsilon greater than 0 such that if delta is greater than 0 and also greater than h, then, so we're taking h and sandwiching it between 0 and delta. We're saying h is sufficiently small. Then the sup of the absolute value, the difference of the function values where x prime and x double prime are chosen from the interval. Here's the h part that matters, x minus h to x plus h. This can be made less than epsilon. Well, now we define the oscillation as a limit as h approaches 0 from the positive side of this stuff in the parentheses. Just highlight that. If you have the oscillation defined as the limit of this stuff, then, and say the oscillation 0, that means I can make that highlighted stuff as little as I want, less than epsilon, by making h sufficiently close to 0 and on the positive side. So I can make the highlighted thing less than epsilon by making h less than delta and greater than 0. It's a one-sided limit. And that's exactly what we say. So for any epsilon greater than 0, we can make the highlighted quantity, there it is, we can make it less than epsilon. Notice it's non-negative because it involves a bunch of absolute values. We can make that less than epsilon by making h sufficiently close to 0, within delta of 0, and on the positive side of 0 because it's a one-sided limit. So that translates oscillation equals 0 into an epsilon delta thing. It's the definition of oscillation and the definition of limit, the epsilon delta definition of limit. So if we've got x minus y, an absolute value less than delta, and in the domain of the function, remember x is fixed, so we're saying y is within delta of x, that's what that amounts to. Then we've got f of x minus f of y, f of x minus f of y, an absolute value less than epsilon. We've got, in other words, if we've got y satisfying x minus y is less than delta, so that means in terms of the h, we're taking y values within h of x under these conditions. Then we get the function values as given here. We get the function values less than epsilon. We had a sup of the difference of function values less than epsilon. So here we get the absolute value of those less than epsilon. So in other words, if y is sufficiently close to x, we get f of x minus f of y, an absolute value less than epsilon. Well, that's the definition of continuity, the epsilon delta definition of continuity at point x. So if the oscillation of f at x is 0, then f is continuous at 0. Conversely, suppose f is continuous at x. Now we're going to show the oscillation is 0. So continuity if and only if oscillation is 0. We want to introduce this oscillation stuff to deal with the set of discontinuities of that function, ultimately showing apparently that Riemann integrability is the same as having the set of discontinuities have measure 0. We'll access the set of discontinuities using, using this result here. So conversely, suppose f is continuous at x and let epsilon be greater than 0. Then there exists a delta greater than 0 such that if the absolute value of x minus y is less than delta, and these are chosen from the domain of the function, that implies the absolute value of x minus the absolute value of y is less than some little positive amount. I choose the positive amount to be epsilon over 2. So this is the same thing you do in calculus when you say we've got continuity at point x. If y is sufficiently close within delta of x, then f of y can be made, give me the positive number, let's use epsilon over 2. F of y can be made within the distance epsilon over 2 of f of x. The only little difference from calculus 1 is the fact that they've taken x and y to be in the domain of the function. The Kirkwood book, and usually most analysis books, will approach it this way. So there's not an idea of looking at values that aren't in the domain of the function. It has implications about one-sided limits versus two-sided limits. What we have here would be, provided we take input values from the domain of the function. This is just the epsilon delta definition of continuity. So continuity at point x would imply this in terms of epsilons and deltas. So if we take an x prime and an x double prime from x minus delta to x plus delta, then we know that the absolute value of f of x prime minus f of x double prime, let's do a little trick here. Let's add and subtract f of x inside here, use a triangle inequality to express it as this. And now we've got exactly this kind of thing. We know that x and x prime are from this interval. We know when we get x, when we get y within delta of x, which x prime would be being in this interval and which x double prime would be from being from this interval. Then we get f of x minus f of that kind of y, in this case x prime. In this case, in the second part, x double prime, this is less than epsilon over 2. This is less than epsilon over 2. Add them together, we got epsilon. What we've shown is that provided x prime and x double prime are from this interval, intersect the domain, then the absolute value of the function values is less than epsilon. So when you take a soup over all such function values, you'll get something less than or equal to epsilon. We get the or equals 2 thing again, but that's good enough to show the oscillation of f about point x equals 0. What we're going to do from here is take a limit as h approaches 0. And we've already looked at a situation where we're taking the h values to be less than delta if we go through and do that kind of limit thing. So the oscillation is 0 if the function is continuous. If the function is continuous, the oscillation is 0. So oscillation being 0 is equivalent to the function being continuous. Okay. Now we got the equipment to go through and prove half of the Riemann Lebesgue theorem. We'll prove it in 2 pieces. And part A of the Riemann Lebesgue theorem says, consider a bounded function f defined on the interval from a to b. That's no constraint because we're about to talk about Riemann integrability, and that's where everything starts in terms of defining the Riemann integral. So bounded function on an interval from a to b. Riemann only integrates over intervals from a to b. Oh, I guess I take that back a little bit. And things you can base on that. You can integrate over infinite intervals, for example. But it's ultimately all based on integrals over the interval from A to B. You only integrate over integrals in the Riemann sense. They might be bounded or unbounded, but you only integrate over intervals. We'll, with Lebesgue integration, integrate over sets versus intervals. So necessary hypotheses based on the fact we're about to say, if f is Riemann integrable on the interval from A to B, these are the only kind of such functions you consider for candidates initially for Riemann integrability. Then the set of discontinuities of f on AB has measure 0. So if Riemann integrable, then the set of discontinuities has measure 0. You know what has measure 0? The empty set. And we had shown above that if the function is continuous throughout AB, that is, if the set of discontinuities is empty, then the function is Riemann integrable. So you can see how this is related to that. There's maybe a converse somewhere in there, but there's certainly a relationship between the level of continuity and Riemann integrability. So what we're saying is if Riemann integrable, then set of discontinuities has measure 0. In part B, we'll take the converse of that. If the set of discontinuities has measure 0, then the function is Riemann integrable. And then we'll be able to say Riemann integrable under these hypotheses, bounded function on an interval AB is Riemann integrable if and only if the set of discontinuities has measure 0. That's a classification of Riemann integrable functions. So suppose f is bounded and Riemann integrable on the interval from A to B. Let A be the set of x values in the domain of f where f is discontinuous. So we want to show set of discontinuities has measure 0. We want to show A has measure 0. How are you going to show that? By covering A with a bunch of open intervals, the sums of whose lengths is less than epsilon, given an epsilon. Okay, well, saying f is discontinuous at x, we just saw in the previous result, is equivalent to saying the oscillation of f at point x is positive, greater than 0. So the set of discontinuities, set A, is of this form. It's the x values between A and B where the oscillation is greater than 0, about those points x. Well, let's look at something somewhat different. Let's consider A sub k, for k a natural number, to be the x values in the interval from A to B where the oscillation is greater than or equal to 1 over k. So these are x values where I want to kind of think in terms of one-sided limits, where the left-hand limit and the right-hand limit are different. There's a gap in the function and a gap of size 1 over k. Because when k is big, that gap is little, but it's still a gap. And the previous conversation is suitable for informal purposes. I'm talking about one-sided limits. Well, they might not exist. I've got some problems with that. But think of it as the function kind of has like a gap in it of size 1 over k at x for the x values in this A sub k set. So saying the oscillation is greater than or equal to 1 over k is saying, in a very crude sense, the function's got a gap in it of size 1 over k at x. Well, what we can do is union up all these sets A sub k from 1 to infinity. Union these up, that will include all x values where the oscillation is positive. So union these up, the oscillation is greater than or equal to 1 over k. If the oscillation is positive at point x, then it's in one of these sets here. If and only if, in fact, that's how we get the equality of the sets. So we can take set A, the set of discontinuities, and write it in terms of these A sub k sets. The sets where the gap at x, the oscillation is what it is. The oscillation is 1 over k or larger. These are nested sets, by the way. All right, here comes your epsilon greater than 0. We're trying to show, what are we trying to show? We're trying to show the measure of set A is 0. So what are you going to do with this epsilon? I'm going to find a bunch of open intervals, cover set A, actually we're going to cover set A sub k, cover set A sub k with a bunch of open intervals, the sums of whose lengths is less than epsilon. So that's what we're going to use the epsilon for. So let epsilon be greater than 0 and fix k. What we're going to do is show a sub k has measure 0. And then we'll deal with this countable union. We've already said something about countable unions of sets of measure 0. So the short-term goal here is show a sub k has measure 0. That's what the epsilon's for. Since f is Riemann integrable by hypothesis, then there's a partition of the interval AB such that the upper Riemann sum minus the lower Riemann sum is less than epsilon over k. That was theorem 6-6. I should document that. Theorem 6-6 told us we can make upper and lower Riemann sums as close as we want if a function is Riemann integrable, if and only if. Okay, so I choose to make the upper and lower Riemann sums within epsilon over k of each other. K came to us as this fixed natural number. For a given I, if x is in a sub k and it's in the subinterval x sub I minus 1 to x sub I, so we need to start talking about these subintervals because we want to talk about these Riemann sums more hands-on, then I'm going to keep the fonts kind of small so we can see the moving parts as we move through this. So if x is in a sub k and it's in the ith subinterval, given I, then if we'll take capital M sub I of f minus lowercase m sub I of f times delta x sub I, what's up with this? Capital M sub I of f, that was the supremum of the function values on this little ith subinterval. The lowercase I was the infimum of function values as we take inputs from this little subinterval. We actually included the endpoints in that. And then we've multiplied by delta x sub I. Yeah, we defined upper Riemann sums in terms of the capital M's and the delta x sub I's. We define the lower Riemann sums in terms of lowercase m sub I's and the delta x sub I's. We're taking a difference here and a difference there. So we're up to something related to the difference of these upper and lower Riemann sums. Where are we going? We're trying to cover set A sub k, with open intervals and show their sums is less than epsilon. For the given epsilon we already have. All right, so if x is from this ith subinterval, then how far apart could these, let me call them maximum and minimum function values be? All right, they're not maxes, they're sups and nths. How far apart could the function values be? On the ith subinterval, and in, I guess this is what I need to look for, when x is in a sub k, how far can function values be? No, we got the oscillation at f bounded by 1 over k. So how far apart could these function values be? 1 over k. They must be bounded below by 1 over k. So the sup and the nth greater than or equal to 1 over k comes from the fact that x is a point inside set a sub k, where the oscillation is at least 1 over k. So the difference in these function values, okay, there's sups and nths of function values, can be at most 1 over k. So if we look at, picking up here, we said epsilon over k greater than upper Riemann sum minus lower Riemann sum. We had that from the hypothesis that the function is Riemann integrable. How do you write that upper Riemann sum? Sum from I equals 1 to n, capital M sub I of f times delta x sub I. How do you write the lower Riemann sum? Similarly, but you use a lowercase m sub I. When I take a difference then, we'll have this times delta x times the sum here times delta x. Pull the delta x out, write it as a single sum. So write the difference of those Riemann sums. They're with respect to the same partition P, so we're good on that. Write that as a single sum from 1 to n. It's a finite sum. Right, it's a Riemann sum. Well, this is a difference of Riemann sums. Do you know how big the capital M sub I minus lowercase m sub I is? I do. It's oops, excuse me, hadn't used it yet. Sorry, on the wrong track right now. Let's take a subsum of that. Okay, we were taking x in a sub k and x in the interval from x sub I minus 1 to x sub I, the ith subinterval. We're going to sum over not all of these, but some subcollection of these I values. The sum prime indicates a summation over all values of I such that the ith subinterval actually intersects a sub k. The ith subinterval, open, intersect a sub k is not equal to the empty set. So some of these subintervals, right, they were indexed by I. We're summing over I now. Some of these subintervals intersect a sub k, and some of them don't. Those that do include those in this sum prime. It's maybe not all of them. Okay, well, you threw out some stuff, and so whatever's left is going to be a sum less than or equal to. Everything in sight is non-negative. We've got soups minus imps. So this stuff is positive. The delta x sub i's are positive. We're dealing with positive numbers all over the place. Now, the capital M sub I itself may not be, but this difference is. So we've thrown out some of the things in this summation. Those things are non-negative. Throw some of them out, and you get something smaller or equal to. So that's the greater than or equal to right there. We're keeping these. All right. So now we know in this sum prime, we know where these x values are from. And now we can employ this stuff up here. So when we sum over the particular I values to which we have restricted this, then we can say we're taking x values that are in this particular ith subinterval. When we have that, then we get the 1 over k delta x sub I bound on this thing. So this thing is greater than or equal to 1 over k delta x sub I when we choose x both from a sub k and that ith subinterval. So we can replace this with the 1 over k delta x sub I, 1 over k delta x sub I. We were summing over whatever prime gives you. Bring the 1 over k out front, and that produces this equation 3. All right, so if we combine what we have up here and what we have down here, what are we doing? Trying to cover a sub k with open intervals. Keep an eye on the big picture. If we combine equation 2 and equation 3, we'd have, let's see, epsilon over k is greater than the sum prime, and the sum prime is greater than or equal to this stuff here. So we've got epsilon over k is greater than 1 over k sum prime. Cancel the 1 over k's, and you're left with epsilon is greater than the sum prime of the delta x sub i's. All right, any emotional attachment to that? The end is near. What are we doing? Trying to cover a sub k with little open intervals. And the sum of those open intervals, we need to be less than epsilon. Here's the sum of a bunch of open intervals, and it's less than epsilon. So we need to figure out if those intervals are the right kind. So we'll let I be the set of index values in this sum prime. Then if we take the union of the open interval x sub I minus 1 to x sub I, the ith subintervals, as I ranges over that index, capital I, the ones that were in sum prime, then we got an open cover of a sub k. This included all of the I, well, a sub k, except possibly for some endpoints, because we did go to open intervals, because we had to talk open intervals to talk measure. But what we've got is a collection of these little ith subintervals that intersect a sub k. We've got all of them that intersect a sub k in this indexing set, capital I. That's what it means. Maybe some of the others don't intersect a sub k. We're not interested in those. We're ultimately trying to cover a sub k. Oh, yeah, except for some endpoints for some technical reasons. So if you'll take these open intervals, they cover a sub k, except we threw the endpoints out. So we might have a little bit of a problem there with the endpoints. We'll take care of it here in a second, though. And if we'll add up the lengths of these endpoints, add up the measures of those little intervals, that is the delta x sub i's, and it's a sum prime in the notation introduced above, and we just saw the sum prime of the delta x sub i's is less than epsilon. So we've covered a sub k, except maybe for these endpoints, and they may or may not be in set a sub k, but we've covered a sub k with these open intervals, a sub k minus the endpoints, with these open intervals, and those open intervals have lengths that sum to less than epsilon. That means a sub k minus this collection of single points is 0. We covered a sub k with a collection of open intervals, the sums of whose lengths is less than epsilon. Then a sub k, well, minus these endpoints, must have measure 0. What if you throw the endpoints in? We said upstairs that the union of a countable collection of measure 0 sets is measure 0. Now we'll take a sub k minus these endpoints has measure 0. A collection of singletons has measure 0 as well. Wouldn't hurt to show that. Well, it's a countable set. There you go. It's a finite set. So we do have the equipment in the notes to show that. Take a sub k minus these points, union those points in. Now you've got a union of two sets of measure 0, which is a set of measure 0. So a sub k does have measure 0. We wanted to deal with the measure of set A, and set A was the union. It's gone up the top, here it is. It was the union of all of the a sub k's, k equals 1 to infinity. We wrote A as a countable union of things. Good thing it's countable, because we know A can be written as the union from k equals 1 to infinity a sub k. So the measure of A is the same as the measure of that countable union. All the a sub k's have measure 0. So the union is a countable union of sets of measure 0. Theorem 6.9 that we observed above, proved a special case of, tells you set A has measure 0. So if bounded function f on closed and bounded interval AB is Riemann integrable on that interval, then the set of discontinuities, set A, has measure 0. If Riemann integrable, then set of discontinuities has measure 0. All right, let's work on the converse of that. Now, to do so, we need a preliminary result. So we need a preliminary result before proving the other half of the Riemann Lebesgue theorem, the converse of what we just proved. And that's also going to relate to oscillations. Let f be a function with domain AB. Then for any s greater than 0, the set of all x values such that the oscillation of f at point x is greater than or equal to s, call it a sub s, is a compact set. So properties of the function, none except that its domain is AB. This time s is a positive real number. We define an a sub s. It's similar to what we did in the previous proof, except before we had a 1 over k here. It was a rational number. Now it's not necessarily rational. So the claim is we take where the oscillation of f with respect to x, all points x in this domain, where that oscillation is greater than or equal to some fixed positive real number s, that's going to give us a compact set. What's a compact set? One for which every open cover has a finite subcover. What's an open set of real numbers? Oh, that's Heine-Borel says that's one that's closed and bounded. So we can get away, since we're dealing with sets of real numbers, in showing that a sub s is closed and bounded using the Heine-Borel theorem and concluding a sub s is compact. Compact and closed and bounded are different in some pretty exotic settings. We won't go to those exotic settings. You don't go there in senior level analysis, I really doubt. We won't, I don't think we'll get there in real analysis 1. We will in real analysis 2 though. You would in a functional analysis class as well. So we're dealing with sets of real numbers. If we can show a sub s is closed and bounded, Heine-Borel will tell us that that set's compact. So I don't have to go to open covers this time on the a sub s. Okay, we'll show that a sub s complement, the little superscript of a c there means complement, is open relative to the domain, concluding then that a sub s itself is closed relative to that closed set. So a sub s is closed will be the conclusion. Of course, a sub s is bounded. It's a subset of the interval from a to b. So it's bounded above by b and below by a. So we'll have closed and bounded. Heine-Borel will say compact. So the plan is to show the complement is open relative to AB. All right, some good old-fashioned analysis. What's it mean when I say x sub 0 is in the complement of a sub s? Well, a sub s is where the oscillation is at least as big as s. So for that not to happen, for x sub 0 in the domain of the function, AB, we must have the oscillation of f at x sub 0 to equal some value t that's strictly less than s. All right, so what we're having happen here on the a sub s complements is it's kind of a good thing. The oscillation is not 0, but it's little. It's littler than s. That's what it's amounting to. When we go through the proof, we'll have little oscillation on big sets, and we'll have big oscillation, which is bad, but it'll happen on little sets. So good things will happen on big sets, bad things happen on little sets. A common analysis occurrence. Okay, so here we've got the oscillation equal to t. It's less than s. That's what it would be to be in the complement of a sub s. Now t would be, by definition, the oscillation of f at x sub 0. So it would be that limit of the sup. We'd have an x sub 0 here. So we got these x sub 0s intersect the domain. That's exactly what we had as the oscillation of f at x. Except we've got x sub 0s as the center of this little interval here. So by definition, that's what t equals. Now let's let epsilon be s minus t over 2. You can choose epsilon to be anything positive, and we're manipulating, I forget if we're manipulating the sup or the limit here, but I'm choosing epsilon to be a positive value and using the existence, I think, of this limit. S minus t over 2, you sure that's positive? Yeah, t is less than s, so s minus t is positive. We divided it by 2, also positive. So take epsilon to be s minus t over 2. Then there exists a delta greater than 0 based on that epsilon, such that if h is within delta of 0 and on the positive side of 0, so we're taking care of this one-sided limit stuff, then we have the distance from the sup to its limit value t to be less than epsilon. Definition of limit as h approaches 0 from the positive side of that thing equals t. The absolute value of that thing stops right there, minus t, is less than epsilon. The distance from the highlighted thing to t can be made less than epsilon by making h sufficiently close to 0 and greater than 0. Yeah, that's exactly what the definition of one-sided limit would say. That's just a little muddled up because we call this thing epsilon, and the function we're dealing here, ultimately a function of h, is all this complicated stuff with sups and function values of the f function. But we're taking a thing and making it within epsilon of t, and we've chosen that epsilon value for reasons to become apparent later downstream. All right, so that implies, first off, this is a non-negative quantity here. We've taken a sup of non-negative things. So this sup must be less than t plus epsilon. We get an upper bound on it. Take the minus t, move it to the other side, get rid of the absolute values. Okay, to do that, I actually get it sandwiched between negative epsilon and epsilon, but we're taking the upper bound part of it, so we've not taken all the information we have in the previous part. But take the t to the other side, we get t plus epsilon. Here's epsilon, take t plus this thing here. If you like, that would be 2t over 2 plus s minus t over 2 would leave us with t over 2 plus s over 2. So from the arithmetic, we get this. So for all y sub 0 in the interval x sub 0 minus delta to x sub 0 plus delta, so that's y sub 0s that lie inside here, we've got the oscillation of f about y sub 0 by definition to be this limit here, to be less than, we took a sup, we took a limit there, so we pick up an or equals to, less than or equal to t over 2 plus s over 2. If y sub 0 is in here, then we know for H sufficiently small, we get this kind of behavior. You already know that, let's see, T is less than S. There it is right at the top. If I point at it, that black bar is going to pop up. T is less than S. So T over 2 is less than S over 2. And we can draw the conclusion that we've got something less than S here. So what we've shown is there exists a delta such that if Y sub 0 is within delta of X sub 0, then the oscillation of F about Y sub 0 is less than S. All these Y sub 0s then lie in A sub S complement. The oscillation is strictly less than S. That happens when you're in A sub S complement. By the definition of A sub S, as points where the oscillation is greater than or equal to S. So in other words, if X sub 0 is, where do we start? X sub 0. If X sub 0 is in A sub S complement, then blah, 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 there exists a delta greater than 0 such that for all Y sub 0 within delta of X sub 0, we have Y sub 0 in A sub S complement. So we've shown this interval, intersect the domain of F, is a subset of A sub S complement. So if X sub 0 is in A sub S complement, the stuff nearby it is in A sub S complement. Remember, the domain's just an interval from A to B here. That is, A sub S complement is open relative to the interval from A to B. So A sub S is closed. A sub S itself is closed relative to the interval from A to B. We know A sub S is bounded. It's closed relative to A to B. It's closed itself as well, since this is a closed set. Relative open and closed behavior. So A sub S is closed and bounded. Then A sub S is compact by the Heine-Borel theorem, and that's what we wanted to show. All right.